So far in this class, we've talked about scalar multiplication, we've talked about matrix multiplication, but one thing we haven't talked about is vector multiplication. And so what we're going to talk about today is the idea of vector multiplication. And the problem is there's two different ways to define vector multiplication, two different ways that we can think of it. If I just take a vector u and try to multiply it by a vector v, this doesn't really make sense because vectors are columns, or we typically think of them as columns. And so if I think about trying to multiply two columns, I can't do that. They're incompatible dimensions. So we can make modifications to make this make sense. So there's two ways we can do that. One is we've got some vector u that let's say is u1, u2, u3, and a vector v that is v1, v2, v3. To make this compatible, so that I can say u times v, I could define that as u transpose, now it's a row vector, times v. And this is in fact how we define this product. This is the dot product, and it's denoted with a dot between them, between the two vectors. This is also called an inner product. I could also move that the transpose to where it's outside. So I could say u multiplied by v is equal to u v transpose, and this would also make it a legally defined product. This is called an outer product. Of the two of these, the inner product is the one that gets used a significant amount. The outer product is really not important for us. So just so you know, we will talk about the inner product or dot product. There is also an outer product, but it's not something that is super important for a introductory linear algebra class. So the dot product is the piece that is going to be important. So the dot product or inner product. So let's give an example. Let's actually compute an inner product and see how we do this. Because yes, we can think of it as matrix multiplication, where we take the transpose of the first vector and multiply it by the second vector. But that gives us a one-by-one matrix when we're done. We usually don't think of it that way. We usually just think of the inner product is just going to be that matrix without the matrix. So it's going to be the scalar. So what does that mean? Well, u dot v is going to be equal to u1, u2, u3 times v1, v2, v3, which is equal to u1, v1 plus u2, v2 plus u3, v3. And technically this should be as a one-by-one matrix. But we usually do not bother to write it as a matrix, and we just call it this scalar, this number. And we could do this for any size vector. Now they do have to be the same size, but this is a three-dimensional vector, three different numbers in it, times a three-dimensional vector, or dot product or inner product, a three-dimensional vector. And we can just write it down like this. It is much faster you don't have to write it out this way. I could have just said u dot v is equal to, and I can just start reading them across. u1, v1 plus u2 v2 plus u3 v3. Notice if I do this the other direction, v dot u, I get v1 u1 plus v2 u2 plus v3 u3. But these are the same thing because now we're talking about scalar multiplication, and the order of scalar multiplication doesn't matter. So we have our first significant result on the dot product is that u dot v is equal to v dot u. And we can go ahead and do this same basic idea and develop a whole set of theorems about the dot product. So let's go ahead, and I'm not going to prove each of these, but they are pretty straightforward if you just start doing them yourself. So let's let u, v, and w be vectors in Rn. Just as a reminder, that means there's going to be n numbers in them. And let C be a scalar. Then our first result, A, was that u dot v is equal to v dot u, no matter what u and v are. The second result is if I take u plus v dot w, this is equal to u dot w plus v dot w. The third result is if I take the scalar c times u and I dot that product with w, I get c, the scalar c times u dot w, which is equal to u dot the scalar c times w. So if I'm dealing with a scalar as well, I can put it anywhere I want to in the multiplication. And the last one is if I look at u dotted with itself. So if I take any vector and I take the inner product with itself, then I get an answer that is greater than or equal to 0. And u dot u is equal to 0 only if and only if, u is the 0 vector. So I wanted to look at that last one for a second. So if I think about u dot u, so I'm going to say let's let u equal, let's do our example working in and say R4. So u is equal to u1, u2, u3, u4. If I look at u dot u, that's equal to u1, u1 plus u2, u2. Let me be more careful than this. So if that's my u, then u dot u is equal to u1, u1 plus u2, u2 plus u3, u3 plus u4, u4. But that's just equal to u1 squared plus u2 squared plus u3 squared plus u4 squared. If I square any number, I get a positive number because a negative number squared is positive. Except 0. If I square 0, I get 0. So the only way this can come out to be 0 is if u1 is 0, and u2 is 0, and u3 is 0, and u4 is 0. So the only way I can get this to be 0 is if my vector is the 0 vector. Otherwise, I'm adding together positive numbers, so I get a positive result. So u dot u is a positive result. What is significant about that is that means I can take the square root of it, because I can take the square root of positive numbers. So we define something called the norm. The norm of a vector is the non-negative scalar that we denote with V, defined by, so we use this double line to denote that we're taking the norm. The double line on each side, it kind of looks like a absolute value, but we're using a double line instead of a single line. And so that double line is defined by the square root of V dot V, which, if we think about what this is equal to the square root of V1 squared plus V2 squared plus dot 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 plus Vn squared. This implies that if I take the norm of V and square it, I get V dot V. So we have something called the norm. I want to look at an example of a norm and to see if we can figure out what it tells us. So let's work in R2 because it's easy for me to draw things in vectors in R2. And so I'm going to think about the vector V equal, let's say, 3, 4. If I want to think about what this vector is, I'm going to graph the vector and so the vector is that arrow going from there to there. And if I look at the norm of V, this is equal to the square root of V dot V, which is equal to the square root of 3 times 3, 3 squared, plus 4 squared, which is equal to, well, the square root of 9 plus 16 is equal to the square root of 25 is equal to 5. So, what does that 5 represent? Well, if you think about where everything is, I can draw a right triangle with side length 3 and 4, and if I use the Pythagorean theorem, 3 squared plus 4 squared is 25, so this is the square root of 3 squared plus 4 squared, or 5. The norm of the vector is the length that the vector takes up. And this can be generalized to higher dimensions. The norm represents what the distance is from the origin to the head of that vector. So you're just taking that vector and you're figuring out what its length is. Okay. What this does is it gives us a way to think about some very specific ideas. So if I think about like taking a vector and multiplying by a constant, what that does is whatever that constant is, I can think about it as changing the length, but not the direction. So it's V, this vector is V scaled by C. So we've scaled it up, it's going the same direction, it's just longer. Or if C is negative, then we've scaled it and flipped it to the opposite direction, but it's still along that same line. Or if C is less than 1, between 0 and 1, then we've scaled it down to something shorter. And so what we can do is we can talk about some very specific important vectors, and those are vectors that are called unit vectors. And a unit vector is a vector of length, or norm, 1. So if I have some vector, like my vector v, that is equal to 3, 4, we just calculated that it has a length, or norm, of 5. So I could turn this into a unit vector by scaling it by the constant 1/5. So if I take 1/5 times v, I'm going to get 3/5, 4/5, and that should have a length of 1 because I scaled it by 1/5 when it had a length of 5. But let's double check and make sure that this actually worked. So if I calculate the norm of 1/5 v, that's equal to the square root of 3/5 squared plus 4/5 squared is equal to the square root of 9/25 plus 16/25 is equal to the square root of 25/25 is equal to the square root of 1 is equal to 1. And so it works. We can scale, and we can turn any vector into a unit vector by scaling by 1 over the length. And this allows us to start to think about other processes. So we can say, I have two vectors, u and v, in Rn. And I'm going to build this with an example. So the example I'm going to use is, let u be 7, 1, and v be 3, 2. If I want to find the distance between them, well, to find the distance between u and v, I can think about the subtraction, u minus v, and that's a vector that goes from one to the other, that is the difference. And if I look at the length of that, the length of the difference is going to be the distance. Let's see that in practice. So our example has, we need 1, 2, 3, 4, 5, 6, 7. Then we need at least 2 and at least 2. So if I'm looking at u and v, my vector v was 3, 2, so that's 1, 2, 3, and 2. That's this point. And my vector u was 7, 1. That's this point. And so if I look at u minus v, so this was v, this one was u. So if I look at u minus v, that's this vector. And so that vector is going to be the distance between these two vectors, between the arrowheads on these two vectors. And so that distance uv is going to be, we take the norm of u minus v, which is equal to the norm of the vector 7 minus 3, 1 minus 2, which is the norm of the vector 4, -1, which is equal to the square root of 4 squared is 16, plus -1 squared is 1. Gives me the square root of 17. So the distance between these is, according to this, the square root of 17. Let's check and see if that actually makes sense on our diagram. So if I take my diagram, I can make it into a right triangle that has a length of 4 and a height of 1. So by the Pythagorean theorem, the hypotenuse has a length of the square root of 1 plus 4 squared is the square root of 17. And so it matched. So this allows us to build a idea of distance, and that can be, now we can take that idea of distance and make it and use it in any number of dimensions we want, because we now just have it as a way to calculate it. So the next really big idea is the idea that we want to be able to think about perpendicular. So if we have a line, we can think about a perpendicular line being at a right angle. And so that's kind of the idea. But we can define perpendicular. Well, the analog to perpendicular in higher dimensions is what we call orthogonal. And so the idea of an orthogonal vector is that two vectors are orthogonal if the dot product or the inner product, so U and V are orthogonal if the inner product or dot product, U dot V, is equal to 0. So what this is telling us is if we take two vectors that are orthogonal and we look at putting their dot products together, what do we get? Well, everywhere where the vectors exactly counteract each other. That is, the distance from along that vector is minimized by using this. Let me say that again. The idea is, if you have some vector u, let's say it looks like this. This is my vector u. And I take the dot product and it comes out to 0, it means that the dot product is looking like this. So if I have a vector whose dot product with that comes out to 0, it means we are looking like this. And this is because if we look at the distance between u and v, or rather between u and negative v, we can start to look at these distances, and these distances are always non-negative, but physically that the distance comes out the smallest, this distance becomes the 0, the smallest it could possibly be, when they are exactly at a right angle. It's not super important that you that you can make that argument. What is important is that you understand that things are orthogonal if u dot v is equal to 0, and that represents perpendicular. Orthogonal and perpendicular are the same basic idea. And so this idea of orthogonal vectors allows us to think about, well, a perpendicular means that you're at a 90-degree angle. And so this orthogonal is also going to mean something along the lines of you're at a 90-degree angle. And so if we think about the Pythagorean theorem, we can look at the Pythagorean theorem and say, well, the distance between two vectors, and so you might say, well, shouldn't it be minus v? Well, we're actually looking at the distance between u and negative v, which makes this u plus v, squared is equal to the length of u squared plus the length of v squared minus something. And so algebraically we can develop this. If this something is 0, then we are orthogonal. And that something comes out to be 0 when u dot v is 0. If that something is not 0, then it actually turns out to be 2 times u times v. So it's 2 times the length of u times the length of v times the cosine of the angle between them. This is called the law of cosines. What is significant about this is it allows us to define an angle, and if we do some algebra with that, we end up getting that the length of u times the length of v times the cosine of theta is equal to u dot v. And when cosine is 90 degrees, that means that u dot v is equal to 0. That is the big ideas for this section, section 6.1 in the book. And I think we are going to stop there.